Assalamu alaikum wa rahmatullah. Good day, everyone, and I welcome you all to our today's physics class. Well, in today's physics class, we are going to learn mechanism of electrical conduction in metals. Okay, as an introduction, remember in our study of basic science when we were in secondary schools, we were told that one of the characteristics of metals is that metals are good conductors of electricity. We were told that without any explanation. Why, guess what? The purpose of this class is to explain how. We are going to explain how metals are good conductors of electricity, how they conduct electricity. That is the purpose of this class. Also, we are going to derive the formula for calculating electric currents in metals. If I have a conducting wire, suppose this is a conducting wire, okay, and charges flow through this wire for some time t, since the charges are flowing, they must generate electric current. So if I want to get the magnitude of that current I, okay, generated after a given time, how do I calculate that? What is the formula? How is this formula related to the charge carrier density, the cross-sectional area of the wire, the drift velocity, and the elementary charge? These are what we are going to learn today. May Allah be with us. Okay, let us give it a start. Um, Suppose you have a conducting wire. Let's say this is a conductor. I'm going to use copper as an example. In general, metals, apart from the metal bond that we have, metallic bond that we have electrons, of course, participating in the bonding. But apart from that, metals do have what we call free electrons. There are electrons that are free to move about. They are not bound to the atoms. They are free to move. Each atom contributes one free electron. So there are actually in every metal where you take, every piece of metal, whether in form of wire or whatever, you do have free electrons flowing in them. If you take copper wire, for example, every 1 meter cube volume of the wire, studies reveal that every 1 meter cube of copper wire that you take, you will have 10 raised to the power of 29 free electrons moving about freely in that material. But this is not enough to generate electric current. First of all, why are they even moving freely? Because they have thermal energy. Okay, the energy in the surrounding is enough to cause little drifting in the material, but it's not enough to cause electric current. Why? This is because the drifting is random. They move randomly without preferred direction. So to make them move in the same direction, you need to apply potential difference. This means that I need this wire, this end of the wire, let's say I connect it to the positive terminal and of a battery, for example, and then this end of the wire I connect it to the negative terminal of battery. Okay, what happens? Here we are going to cut a given portion of this wire and explain what happens. We are going to magnify it. Okay, if I cut this portion, then if I magnify it, we know that wire is cylindrical. So this is what we are going to find. Okay, something like this. When you magnify it, this portion, this cut portion, this one, it has area that we call cross-sectional area. A. This is the cross-sectional area, cross-sectional area, and is denoted by A. Now, let's call the length of this wire from here to here. We're going to call it D. This is the length of the wire. Okay? Again, you do have electrons. Okay? You do have electrons inside the wire. Inside the wire. Okay? Before connecting this to positive and negative terminal, the electric field in the wire is not uniform. By the time you connect this to positive terminal and then this to the negative terminal, you are now creating uniform electric field inside. Okay, and we know the direction of electric field is from the positive to the negative. So inside this, you have electric field, okay, in this direction. From this is positive, this is negative, don't forget. So I have electric field in this direction. Now, the electrons inside, remember we are considering only the free electrons, because only free electrons generate current in the metals, not the bound electrons, not those that participate in chemical bonding. No, not those ones. Okay, now let me ask, in which direction do you think this current will move? The current will move in the direction of the positive terminal here. You see that? This is because electrons are negatively charged. They will be attracted by this positive and then they will be repelled by the negative end. You see? So they drift in a direction opposite to your electric field. The drift in this direction, all of them drifting in this direction. This is enough to generate current. Okay? And because they are drifting, they have a velocity that we call drift. They have a velocity that we call drift velocity, okay, denoted by V. They have drift velocity. Now, we're going to do something here. Let's say the number of electrons that you have, meaning the total number of electrons that you have, let it be n, meaning in this portion, the entire electrons that I have, free electrons, number of, let's call this free, number of free electrons that I have is capital N. Okay, now the volume of the material, okay, we have to get the volume here. This is cylindrical. The volume of a cylinder is cross-sectional area times length. So we are going to multiply A and D to get the volume. So let's say volume comma V equals A here multiplied by D. That's our volume. Okay. Remember, each electron has a charge that we call elementary charge. So our elementary charge is E, okay, is given the letter E in the lower case, and the magnitude is 1.60 times 10 to the power of minus 19 in Coulomb. Okay? Okay, now we are moving on to something interesting. Now, if you take number of free electrons divided by volume, okay, meaning the entire free electrons that you have here, all of them denoted by capital N, divided by the whole volume of this material, and that volume is V, which is AD. This will be equal to what we call charge carrier density. The charge carrier density is the number of free electrons you have in 1 meter cube volume of the material, and is denoted by small letter n. So is denoted by small letter n. Yeah, it's written. So number of free electrons, in symbols we can write capital N here, divided by the volume is V, so we put V here is equal to N. So from this relationship, I can make N the subject of the formula, and N becomes this times this NV. Okay, moving back, you can see that our V is a D. Our V is a D, so this is equal to N. Instead of V, I can write a D. So the number of free electrons that I have is given as NAD. Okay, okay. The next thing we should know is that since this is the number of free electrons that we have, and we know that each electron has this charge, so we can multiply this and this to get the total charge. Can you see that? Every one electron, every single electron that you have possesses this charge. So if I have n electron, if this is the total number of electrons that I have, when I multiply n by E, I will get the total charge that they have. So total charge denoted by Q is equal to NE. Can you see that? NE. Now, this means that since my N is this, I can take all of this and put it here for N. So I will have NAD. This, all of this is my N, because this formula says N equals this. So now I bring my E. This is the total charge. You see that? This is the total charge. Now, how do I get the current? Remember, I told you that one of our performance objectives is we want to get the magnitude of current flowing through the material. So our current, I remember from our previous video that current is charge divided by the time. Charge divided by the time. Okay. Coming back to this, let's say I have an electron here from this end, and the electron drifts from this end to this end. Can you see? It drifts from this end to this end. The total distance traveled is d, and the time it takes is t. Okay? Now, it has drift velocity, and remember the velocity should be this distance in this direction, which is displacement. It is displaced from here to here, so its displacement is d, and the time it takes to move from here to here is t. So your v is d over t. Don't forget this, we are going to use it here. V is d over t. This means here, coming back to here, I can say this is equal to, you will see why I went back to that. Your Q is this, right? So you can take all of this and put it here for your Q. When you do that, you are going to have NADE divided by T. Now look at this expression. Look at it. I have D over T here. This one that I have here, D over T, D over T, D upon T is my V. So instead of D upon T here, I can put V there so that my current becomes N E, and then instead of this fraction, I can put V here for the drift velocity, and then I put my E for elementary charge. So with this, I have derived the formula for calculating the current. So I conclude that my I, therefore, my I is equal to N A V E. This is the formula we use to calculate the current flowing through the conductor. Okay, where this M, as we said, is the number of electrons in 1 meter cube of the material. If this is the material, let's say I cut 1 meter, this portion that I have just cut off has a volume of 1 meter cube. then the number of free electrons in this region, that is just 1 meter cube, we call that number n. We give it a letter, small letter n. And then this capital A is the cross-sectional area of the wire. Okay, I didn't tell you the unit of A, the unit of n. The unit of this n is per cubic meter, per cubic meter, okay? Then V is the drift velocity, and the drift velocity is measured in meters per second. The drift velocity is usually small, it's not that large, okay? Because the drifting is small. They drift slowly, not that fast, okay? So this value is usually small. Finally, E. Your E is a constant, is the elementary charge E, 1.60 times 10 raised to the power of minus 19 coulomb. Okay, here is the summary. Here is the summary. First of all, if I have a conducting wire, okay, that is a metal, okay, the metals have free electrons in them. We have electrons that do not participate in chemical bonding. They are free to move about in the material. But that motion caused by thermal energy that they have from the surrounding is not enough to cause to make them generate electric current, because they move anyhow without any preferred direction. The electric field in the material is not uniform. So you need potential difference, okay, to create uniform electric field in the material. And when you achieve that, the electrons will now drift in the same direction. That way you can generate electric current. And this is why the wire must be connected to electricity source, to a voltage source. So after that, then we have this diagram to show that we magnify our wire to show that this is how it looks like. It is cylindrical, and we have free electrons. Only free electrons are used. Bound electrons do not generate current. Now, this is the negative terminal, this is the positive terminal, and your electrons drift from the positive to the negative terminal, while the electric field is directed from the positive to the negative terminal. So there is opposite direction here. The electrons drift in a direction opposite to that of the electric field you created. Then you said the number of electrons, the total number of electrons that you have here is denoted by N. The volume of the material V is area times the length D, AD. Then the elementary charge, each electron carries this charge, E equals 1.60 times 10 to the power of minus 16 coulomb. Now, this ratio is important. Number of free electrons divided by volume, meaning the total number of free electrons that you have here divided by the volume of the material, and this fraction is called charge carrier density, and it is the number of free electrons in 1 meter cube volume of the material, denoted by small letter n. Now in symbols you can write capital N for this number of free electrons, capital V for the volume, equals the small n. Now make n the subject of the formula, simply multiply n by V and you have NV. Remember previously that we said this V is AD. So instead of V here, you put AD here, your expression becomes NAD. Then to get the total charge, remember that since this is the number of electrons, each electron, a single electron, has a charge of E. So when I multiply my E by N, their number, I will get the total charge. So total charge Q equals NE, and my N from the previous formula, my capital N is NAD. So instead of N, I put NAD, then I bring my E here. This is the total charge. Finally, I want to have the formula for current. I want to get the formula for current. So I will say current I equals Q upon T. This is from the previous video. The charge divided by the time it takes this charge to flow through the material. Okay? So your Q is NADE. So when you put that NADE divided by T, because this one now is substituted for this. Now, coming back to the material, since the electrons are drifting from this end to this end, assume that an electron moved from here to here at distance d in a time t. Its drift velocity is given as d over t. Now, if you bring this idea to this formula, you will see that you have d over t here that you can put v to stand for it. Okay, so this is why we say instead of d over t here, we can just put v so that our current I becomes NAVE. Now, at the end of the day, we have current equals NAVE as the formula for calculating our current in ampere. I hope you enjoyed this class. Thank you for watching.